Okay, this is section 8.2, the sine and cosine curves, and our objective today would be to find equations of different sine and cosine curves and to apply these equations. So today we're going to study the concept of amplitude and period, and we studied those earlier in our unit on functions, but now the application in trigonometry is really useful in application problems. So become an expert at this stuff today. So the graph of y equals any scalar multiple c times f of x, a function, can be obtained by vertically stretching or shrinking the graph of y equals f of x. So if we multiply by the c, we're only affecting the function vertically, not horizontally. So that's going to change the amplitude of our function. So to kind of play with this, let's graph the first period of y equals sine of x on our calculator. All right, so get out your graphing calculator and start off with, let's decide, do we want our x intervals to be in radians or degrees? And you know, as we go farther and farther into advanced mathematics, more and more often we're going to be in radian mode. So let's go ahead and go radian. So make sure you hit the mode button on your calculator and make sure radian is highlighted right there. Then go ahead and go to your y equals button and make your y sub 1 sine of x. Okay, now if you hit the zoom button, all right, you can get all kinds of really cool windows here. And I'm going to look, so zoom, and you see number 7 right here. This is a trig window, and this trig window has an x interval of a little beyond negative 2 pi to 2 pi. And that's going to give you a graph like this. Okay, so when I want a typical trig function, more often than not, I just go to my trig window, just like that. Okay, now they want us to graph the first period of y equals sine of x. And I hope you guys at this point know that the first period would be, well, that's pi over 2, pi, 3 pi over 2, and 2 pi right there. All right, so the first period of y equals sine of x would be in the interval from 0 to 2 pi. So let's change our window right here, and all I'm going to do is hit my window button, and I'm going to make my x min 0 and my x max 2 times pi. I'm not going to mess with anything else. So let's see what this looks like. And there's what I have right there. Okay, now this is a great picture of y equals sine of x beginning at the origin, and then it has a max of 1 at pi over 2, and then a 0 at pi, and then a min of negative 1 at 3 pi over 2, and then we have another 0 at 2 pi. Okay, so get to the point where you see this graph whenever you see y equals sine of x. See it in your mind. All right, now let's visualize y equals 2 times sine of x. What do you think the scalar multiplier of 2 is going to do to this function right here? All right, so easiest way to picture that would be, let's picture some key points on this first period of sine of x right here. All right, and I chose the points that are my zeros, which is 0, pi, and 2 pi, and then the max and the min. Well, if I take that function and I multiply it by 2, all I'm doing is changing the y coordinates of every point on that graph. Well, all of them except for the zeros, of course, because 2 times 0 is 0. All right, so I'm picturing the max to go from a 1 up to a 2, and the min to go from a negative 1 down to a negative 2, and the zeros will stay zeros. And there it is right there. Okay, now y equals 2 times sine of x has amplitude, and you can see the amplitude right now, but I want to give you the formula for amplitude that I gave you earlier in the year. Okay, amplitude is always the max, which we use a capital M for, minus the min, lowercase m divided by 2. So if you look at this now, the maximum is a 2 right there, and the minimum right here is a negative 2. And if I go 2 minus negative 2, I get a 4, and 4 divided by 2 is 2. So this function has an amplitude of 2. Okay? The original sine curve had an amplitude of 1. Okay, graph the first period of y equals cosine of x on your calculator. So just go to your y equals button, and let's change our sine of x now to a cosine of x. And we already have a great window set up and everything, so let's just leave it at that and hit graph. Okay, and now sine starts at the origin, but cosine starts at the y-intercept 0, 1. Okay, now let's play with the amplitude of this function. But by the way, right now, this curve has an amplitude of 1 because it has a max of 1 and a min of negative 1. And 1 minus negative 1 would be 2. 2 divided by 2 is 1. But now they'd like you to visualize y equals 1/2 of cosine of x. Okay, so I have a scalar multiple of 1/2 now. What is that multiple going to do to the function? Again, it's going to take every y coordinate on that graph and multiply it by 1/2 or divide by 2. So see these points right here? Okay, I'm picturing this max of 1 to drop to 1/2, and the zeros will stay 0, but this min of negative 1/2 will slide up to negative, or excuse me, that was a negative 1, and that will slide up to negative 1/2. That 0 will stay the same, and this max of 1 will slide down to 1/2. And there it is, exactly what we're visualizing. This is called math in the mind's eye right here. Okay? Now, let's talk about this. Y equals 1/2 cosine of x has amplitude. Well, my original cosine had an amplitude of 1. All right? Now this would be an amplitude. Think about it. From the x-axis, I'm going up 1/2 in both directions. And if I did 1/2 minus negative 1/2, that'd be 1/2 plus 1/2, which is 1 divided by 2. 1 divided by 2. Again, max minus min divided by 2. And again, 1/2 minus negative 1/2 divided by 2. And you're going to get a 1/2 right there. This is so cool. All right, now we're going to take our scalar multiple of 1/2 and we're going to make it the opposite of that 1/2. So what do you guys think this negative is going to do to this function right here? Okay, well, let's think about those key points again. If I take that graph of 1/2 cosine of x, which we see right here, and I multiply it by negative 1, isn't that going to simply take every y coordinate and multiply the y coordinate of every point on that graph by negative 1? And wouldn't that just give me a reflection in the x-axis? Exactly. So, see this 1? It's going to now be, or excuse me, that's a 1/2 again. That's going to be negative 1/2. The zeros are going to stay the same, and this negative 1/2 will be 1/2. And this 1/2 will now be a negative 1/2. Just a reflection in the x-axis. And there it is right there. Okay, now let's talk about two things. And I haven't introduced period yet today, but we talked about periodic functions in chapter 4. All right, so let's think about this. This function, y equals negative 1/2 cosine of x. Okay, what's the period? How far do I travel before the pattern repeats? And this is a graph of the first period of this function. And this is a pi over 2, a pi, a 3 pi over 2, and a 2 pi. So the period of that graph would be 2 pi. The amplitude, again, max minus min divided by 2. And we already said the amplitude of that would be 1/2. Get really good at period and amplitude. Okay, so now let's talk period. the graph of y equals f of c times x. So this time, instead of multiplying the entire function by c, we're only multiplying the x coordinate by c. Can be obtained by horizontally. Now this is going to do the same thing, except now this is going to affect the graph horizontally. So it can horizontally stretch or shrink the graph of y equals f of x. So when I multiply my x by a number, I am changing the period of the function. That will not affect the amplitude. So let's visualize our y equals sine of x again. All right, picture it in your mind before you graph it. And then let's just graph the first period, so keep your window the same. And this is what I hope you see right there. All right, now let's take this x and multiply it by a number and see what happens. Oh, first let's go ahead and picture cosine too. That's a great idea. So cosine, instead of starting at the origin, has a y-intercept of 1. Looks like that right there. Okay, now the period of y equals sine of x and y equals cosine of x is, and again, how far do we travel before this pattern repeats? Forever and ever in both directions, by the way. And again, that point right there, that x value is 2 pi. The x value over here is also 2 pi. So the period of y equals sine of x and y equals cosine of x would be 2 pi. So the period of y equals sine of 2x. So my c here, up here in this little definition, is a 2. And all you need to know is this. This number right there will always divide the period of the function. So because the period of sine is 2 pi, if I take the x and multiply it by 2, the period of my new function would be 2 pi divided by 2, which of course would simplify to pi. Okay, now let's picture that. So this would be a horizontal shrink right here, because this pattern would be completed in pi units rather than 2 pi units. So I'm just going to shrink that function horizontally, and that graph would look like that right there. Here's the sine curve again, but it's completing that whole period at pi units right there. So that, my friends, is the graph of y equals, oh, and that should not say sine 2 sine of x. That should say y equals sine of 2x. That is a typo on my part right there. So let me fix this. x. Sorry for the little delay, but I just created this. Okay, and it looks like I made the same mistake on the other one here. This should be y equals, and let's put this x in parentheses and go make the c in this one 1/3, and we're going to get there in a second. All right, I hope that cleans up nice for you guys. Okay, all right, I better adjust this a little bit too. Let's make this pretty. How about right there? And how about right there? This is good for you to see because, again, you know, we all make mistakes. But, again, this is what goes into these PowerPoints. I have to do a lot of adjusting. So let's see. Let's get caught up to where we were now and see if everything is nice and clean right there. All right. We were right here. And then we graph this y equals sine of 2x, which had a period, of course, of pi. All right, and then I said that would be a horizontal shrinkage and look just like that. So this, my friends, is the graph of y equals sine of 2x right there. Now, you had a peek of this one, so I hope I didn't blow the surprise. But, by the way, that x value right there is pi. Okay, now the period of y equals cosine of 1/3 x is, now remember, this 1/3 will divide the period of cosine, and the period of cosine is 2 pi, so I'm going to go 2 pi divided by 1/3. And of course, 2 pi divided by 1/3 would be 6 pi. So for this one, this is going to be a vertical stretch, or horizontal stretch, I should say. All right, so this 2 pi is just going to become now 6 pi. So if this is the graph of y equals cosine of 1/3 x, then this 2 pi right here would have to become a 6 pi. Okay, now period and amplitude of sine and cosine curves. Write and highlight this and make sure you understand this. Okay, the functions y equals a times sine of bx and y equals a times cosine of bx, where a does not equal 0. We don't want to multiply our function by 0. And b is a number greater than 0, would have an amplitude. Well, the scalar multiple is a. All right, so the amplitude would always be the absolute value of that a. And it's absolute value because this a could be negative, but the amplitude is a magnitude. And then the period would be, well, the x is being multiplied by b in both of these, so the period of sine and cosine would be 2 pi. So the period of a times sine of bx or a times cosine of bx would simply be 2 pi divided by that b. And there you have it. So, wow, look at this. Give the amplitude and period of the function y equals -4 times sine of 3x. Then sketch at least one cycle of its graph. Okay, so let's start with the easy stuff. Amplitude. Well, amplitude is the absolute value of this a right here, which would be the absolute value of -4 or 4. And this 3 does what? That's right, it divides the period. And the period of sine is 2 pi, so the period of any number times sine of 3x would be 2 pi divided by 3. All right, there's part 1, part 2. And then it says sketch at least one cycle of its graph. And that's another way to say, let's sketch at least one period. And we'll do even a little more. How about that? So, how about, we've been using our calculator a lot. Let's see how we do without our calculator here. All right, so here is my window to graph y equals -4 sine of 3x. All right, so this is going to be way more than one period, by the way. Now, let's think about this. What I'm going to do first is I'm going to visualize y equals 4 sine of 3x. All right, and then we'll deal with reflection last. All right, so now, well, the period is going to change because the period is now going to be 2 pi divided by 3. So if my pi is right here, and let's look at these hash marks, 1, 2, 3, 4, 5, 6. So let me see, this would be pi over 6, this would be pi over 3. That would make this right here my 2 pi over 3. So my entire curve is going to be complete at that x value right there. So it's going to begin here, and it's going to go to that 2 pi over 3. Oh, I missed that hash mark a little bit right there. Now, let's think about this a second. Wouldn't that make this hash mark pi over 3? Okay, and then do you see the amplitude of 4 right here? All right, and again, I'm picturing this down here right now, +4. So that means at pi over 6, I'm going to go up 1, 2, 3, 4. Let's put a point right there. All right, and then at this hash mark, let's go down 4 right there. And that's a great scatter plot for y equals 4 sine of 3x. So there it is right there. And notice I did this dash because they actually want me to graph y equals -4 sine of 3x. But anyway, let's do a couple more cycles here so that pattern would just keep continuing to go in both directions. And I'll go off to the right here. All right, so that's a great picture of y equals 4 sine of 3x right there. But now, what's that negative going to do? Nothing more than a reflection in the x-axis. So the zeros will stay zeros, and my maxes will reflect down and become mins, and my mins will reflect up and become maxes. So visualize that right now. I hope you see this picture in your mind. And there it is. That is our graph of y equals -4 sine of 3x. Okay, now give the amplitude, period, and equation of the curve shown. You want to get really good at this. So now, on the previous slide, they gave us the function and asked us to graph it. Now, on this slide, they're going to give us the graph and ask for the function. So, let's see. Notice how we're not starting at the origin, so I would probably use a cosine for this. And let's think about amplitude. Well, amplitude, isn't that max minus min divided by 2? Again, I'll have you write this again. Memorize this. The amplitude always equals the max minus the min divided by 2. So the max is 3. The min is -3. 3 minus -3 would be 6. And 6 divided by 2 would be 3. So this function has an amplitude of 3. What's the period? How far am I going to travel before my pattern repeats? And it looks like I begin to repeat right there at 8. So the period is 8. So we have an amplitude, we have a period, now we need an equation. All right, so we're using the general form here of a cosine function. Y equals a times cosine of bx. So y equals, and a is my amplitude, 1, 2, 3. And what's this b right here? Now, be careful, that's just not direct substitution like the amplitude is, all right? This b divides the period, so you've got to do a little crunching up numbers here, all right? So remember the original period of a cosine curve is 2 pi, and then this b divides that period. So I know that 2 pi divided by b has to equal the period of this curve right here, which we said was 8. So 2 pi over b has to equal 8. Now let's just solve for b. So that implies, well, if I multiply both sides by b and then divide by 8, I'm going to have b equals, and picture the b over here, and then a 2 pi over 8, which I would write as pi over 4. There we go. So I have my b. I'm essentially done. That implies y equals 3 cosine of, and what was that b again? Pi over 4. And there you go. That is the function for this curve. So you need to be able to go from the graph to the function, or from the function to the graph. Beautiful. Okay, now solve the equation 6 sine of 2x equals 5 for the interval 0 is less than or equal to x and x is less than 2 pi. Give answers to the nearest hundredth of a radian. Okay, final answers. Nearest hundredth of a radian. So when we do our last step, which will probably be an inverse sine, we better make sure we're in radian mode on our calculator. All right, so let's take this beautiful little trigonometric equation and solve for the x. Well, my first thing would be I better solve for the 2x's. So I'm going to get rid of that 6 right there by dividing both sides by 6 to get sine of 2x equals 5 over 6. And now, like I mentioned a second ago, we're going to have to undo the sine function by doing inverse sine of both sides. Okay, and oh, take a look at this, all right? They gave me x is in the half open interval from 0 to 2 pi, but this function is in terms of 2x, so I'm going to need to change this interval. Okay, so if 0 is less than or equal to x and x has to be less than 2 pi, that would imply, look at what I do right here, 2x's. Well, let's just multiply all 3 sides of this double inequality by 2. So I'm going to say 0 times 2 is still 0, and 0 is less than or equal to 2x, and 2x has to be less than not 2 pi, but 2 pi times 2, or 4 pi. So now I need to find all of the 2x's in the interval from 0 to 4 pi is my first step right here. Okay, now let's go ahead and solve for 2x. So by doing inverse sine of both sides. So 2x would be approximately, now get your calculator out and let's double check. I think we're in radian mode, but I'm going to double check. Yes, I am. Okay, and now I'm going to go inverse sine of 5 over 6. So second, the sine button for the inverse sine of 5 divided by 6. Okay, and I'm getting, now I want my final answer to the nearest hundredths. So right now I probably want to go to at least 3 decimal places. Let's see if I did 0.985. Oh yeah, there you go. Okay, now, you know with trig, we're periodic, so there's going to be several values of 2x for which inverse sine is 5 over 6. Okay, so let's go ahead and put this 0.985 on our circle. And again, you guys, 0.985, well, this whole length would be 1.57 right there. So 0.985 doesn't have to be perfect, but let's put it about right there. Now, in what other quadrant is sine positive? Quadrant 2. So if I reflect this ray in the y-axis, I'm going to end up right there in quadrant 2. And now, how am I going to get this angle right here? Well, this would be pi, and I'd subtract from pi that 0.985. So I'm going pi minus 0.985, and that's going to get me back to that terminal ray right there. Okay, so pi minus 0.985. Let's go second pi minus 0.985. Okay, and I'm getting, and I'll go to 3 decimal places again here, and I probably did a 2.157. I did a 2.156, so I just did 4 sig digs there. I gotcha. Okay, all right, that's fine. Now, let's think about this. All right, we just did 1 complete revolution here. All right, and we have those 2 rays. But now we have to go to 4 pi. So I have to do another revolution from this ray right there. So can I just add 2 pi to my 0.985? 2 pi plus 0.985, 2 second pi plus 0.985. My buttons aren't working as well on my calculator as they have. Okay, I'm good there though. And I'm getting 7.268. Okay, good. And now we better do 1 more revolution from that terminal ray in quadrant 2. All right, so that was what? 2.156? So let's go 2 pi plus 2.156. 2 second pi plus 2.156. 2.156. And I'm getting 8.439. There you go, right there. Now, they don't want us to solve for 2x here. We've just solved for 2x. And we have these 4 angles, right? But we need to solve for x, okay? Again, I need all x from 0 to 2 pi. So can I just take each of these answers and to solve for x, aren't I just going to divide every one of them by 2? So, and again, little note up here, punch out 4 pi on your calculator. 4 second pi. And that's going to be 12.566, right? Now, if I did any 1 more revolution, I'd be beyond that 12.566, okay? So, I know, okay, 5.66, and I rounded, okay, 57, that's fine, all right? So, I know I'm done right here. Now, let's take these and divide them all by x. So, x equals, okay, let's go 0.985 divided by 2. 0.985 divided by 2, and to the nearest hundredth I'm getting 0.49. Okay, and then let's take the next one, which was 2.156. 2.156 divided by 2, and I'm getting 1.08. Okay, and then my next answer for 2x was 7.268. 7.268 divided by 2, and I'm getting 3.63. And then finally, 8.439 divided by 2, and I am getting 4.22. And there you go. So there's my 4 angles x that would solve this equation. 6 sine of 2x equals 5. That is so cool. Now, solve the equation, same equation, in the interval from 0 to 2 pi with a calculator. Okay? All right, I want to change one thing on this one too. I want that to be not a big deal here, but I'm going to change this less than or equal to a less than. Okay, there we go. That was an easy fix. So let's go from current slide, and there we have it. Okay, so on the calculator. Now you guys, here's the answers we just had by hand right there. We did crunch some numbers with our calculator, but now we're just going to graph. And you have two options. You could graph 6 sine of 2x as y sub 1 and 5 as y sub 2 and find the intersection points. I kind of like to just make this one function and say, when does 6 sine of 2x minus 5 equal 0? So I'm going to do that. I'm going to make my y sub 1 6 sine of 2x minus 5. All right. And now I need to put this on the appropriate window. So look what I did for my window. All right. I'm going from 0 to 6.28 right there. Okay. And that's fine because that's beyond 2 pi, isn't it? All right. But now look at what I did for my y min and my y max. Now, this 6 sine of 2x would oscillate between negative 6 and 6, but we subtracted 5 from that. So negative 6 minus 5 is negative 11, so I made that my min. And 6 minus 5 would be a 1, so I made that my max. And now I'm going to have a great graph where the zeros will be the solution to this equation. There they are. And again, now you can find each of these very easily on your calculator. I'm just going to pick one of them. All right. So let's check this right here. All right. Which we should get a 3.63. All right. So let me talk you through it, and then I'll give you a picture of it. But if I want to find the zero of a function, I'm going to go second calc. And do you see number 2 is 0? So second calc brings you to that window, and go down and hit 2, and you're going to find your 0. So when you do that, you're going to have this graph, and your cursor is going to say left bound. You just arrow your cursor a little bit to the left of that, hit enter, and then your cursor is going to say right bound. You just arrow to the right until you get to the right of that 0, or in this case above it, and hit enter again, and then your cursor is going to say guess. You just hit enter again, and your calculator is going to give you this, and you see what I see? That 0 right there on this graph is approximately 3.63, so our calculator agrees with the numbers we were crunching on the previous slide. Okay, I'd like you guys to do page 305, problems 1, 3, and then 5 through 10, 21, and 25. All right, and have a great day. Get a hold of me if you have any problems or questions. Thank you.